Science 8. Today we're going to go over how light bends, so refraction. Some of you guys might have come to my experiment last week, and we actually bent light through Jello using different types of lenses. This is kind of an extension of that. So we talked about how light bounces off mirrors and reflects. And today we're going to talk about how light can actually travel through a different type of medium is what we're going to call it. So the difference between air, glass, maybe water can actually cause light to bend or refract. So that's what we're going to talk about today. Okay, so basic recap is light always travels in straight lines. It can be reflected, so bounced off an object that is very, very, very shiny or smooth. It can be absorbed. So this is what gives us the idea of the color black. Or it can be transmitted, so it can go through an object. When light is transmitted, so when it travels through a transparent or translucent object, if it does so at an angle, what can actually happen is it can refract or bend. So we're going to talk a little bit about why this happens and why this discovery happened. So we already talked a little bit about Isaac Newton. So Isaac Newton discovered that white light is a mixture of all of the different colors. So when white light hits this prism, what happens is it refracts and it shows all of these different colors. So he discovered refraction. So we used a prism to separate the visible light, the white light, into many colors. So white light is made up of all different color wavelengths. So when light travels through another material, it refracts or bends. So what happened is this white light hits the prism and all of these different wavelengths are going to travel at different speeds. So the long wavelengths like red are going to bend a little bit less than the violet wavelengths. So they've bent a little bit less. So they're pretty much carrying on in their direction. They're bending just a little bit versus the violet wavelengths have bent quite a bit. So long wavelengths like red bend less than short wavelengths like violet. And this causes the colors to separate and show the rainbow. So this is refraction that's happening here. So that allows us to see that visible light is actually composed of all of these different wavelengths. So when we see white light, for example, when you flick on the light in your bathroom or in your kitchen, you see white light, but what is actually happening is you just can't see that that white light is composed of all of these different colors until it travels through a medium at an angle like that. So another thing Newton discovered that was kind of interesting we didn't talk about last time is he decided to place a second prism on the other end. So he's got his white light traveling through, it separates out and it's refracting, so you can see all the different colors. So he placed a second prism. What do you guys think happened to the light on the other end of this second prism? So what ended up happening is that light, the colors end up actually recombining, so they refract, they bend again, and they come out the other side as white light. So they recombine and turn into white light. So this prism allows us to bend those back out so we can see all the colors. This prism bends them back together and turns into white light. So if we refract something twice, it'll return to its original state. So this explains how rainbows form. So rainbows usually occur, as is in the title, after rain. So what happens is the sunlight finally comes out after a big storm. There's maybe a little bit of water or kind of particles of water in the air. Sunlight hits the water, and what happens is inside that white light coming from the sun, it refracts. So it bends within the raindrop and then it reflects back out, and that's how your rainbow is actually created. So basic understanding of refraction. So refraction is the process in which light changes direction when it moves from one medium to another at an angle. So one medium to another at an angle. When I mean one medium, I'm talking about a different material. So we don't necessarily think of this as a different material, but this light is actually traveling through air right now. then it travels through two subsequent materials. It travels through the glass, and then it travels through the water. Every time it changes material, it's going to bend a little bit. And this is going to happen visibly when we do it at an angle. So you can see that the light was traveling straight, and then what happens here is the light kind of seems to bend upwards a little bit and then bend back down. So even though we know light is still traveling straight, the medium is going to make it appear bent. So example, light bends as it moves from air to glass to water and then to air. So why does it do this? Why does it bend when it's traveling through these different, we call them mediums? I got this. So we've got our incident ray. We're not going to get too into this vocabulary. The incident ray is the one incoming. Refracted is the bent ray. And then it bends again here because it's changing mediums. That's going to be another refracted ray. So we've got three different bends here. We've got the one coming from the glass, the one coming from the water, and the one coming back from the air. So refraction causes the path of light to bend when it travels from one medium to another. So we've got our beam of red laser light. This is just the thing that we're measuring it up against. It's just a 90-degree angle. So we call it the normal, but it's not super important. So we got our light coming in. So we see the arrows are coming in this way, coming in at this specific angle. And then on the other side, when we hit the water, it's going to cause a slight bend when it's traveling through this medium. The opposite is also the case. So if we had, for example, a pool light, the light's going to travel up from the water, and then it's going to bend when it hits the air. So once light enters a new medium, such as water, it's going to continue to travel in a straight line, but as soon as it hits a new medium, it's going to bend a little bit. So why does this happen? I like to think of this diagram of soldiers. So if you've got a bunch of soldiers marching through the grass, they're going to be able to move quite quickly. As soon as they get into a sticky patch of mud, what's going to happen is they're slowly going to bend. They're going to slow down. So if this guy's traveling slower, this guy's going to have to travel slower as well. And each of those guys traveling slower is going to cause the person behind them to walk slower. So that's going to cause that bend. So when light travels at different speeds, so it's traveling at different speeds in different media, so light can travel faster through air than it can travel through glass, or than it can travel through water, it changes direction. So we call this refraction when it changes direction. So when it has to slow down to enter a new medium, it's going to change direction and it's going to slow down. So light travels slower in a more dense medium than a less dense medium. So air is obviously easier to travel through because it's less dense. It's not weighing you down than something like water. So imagine walking 20 meters across a field that's just filled with air. What's easier, doing that or swimming 20 meters across a pool filled with water? So water is a more dense medium. It's harder for you to travel through, and it's also harder for light to travel through. It's just harder for us to see. So refraction is really cool because it can actually play really weird tricks on your eyes, and it can make things appear bent. So because the eyes cannot tell that light has bent, they kind of play these little tricks on you. So your brain is always going to assume that light is traveling in a straight line, but then when it doesn't, it's going to kind of play this illusion on you. So what I'd like you to do is I'd like you to spend some time doing these labs, 1 and 2, and I'm just going to explain this concept here. Another thing that light can do when it's traveling to a different medium, so for example, this fisherman is trying to catch this fish. He's got his javelin. He wants to hit the fish, but what happens when you see something refracted? It can play tricks on your eyes, as I mentioned. The fish is actually, because your eyes are assuming that light is traveling in a straight line, the fish is going to appear as if it's here. So straight ahead, just like the light's telling. But what actually happens is that fish is going to appear a little bit lower. So what's happening is this fish is seeming to appear here. It's just an illusion because your eyes can't tell when light is bending. So because this light has traveled from the air, which is a less dense medium, to the water, which is a more dense medium, the real position of the fish is not what you see when you look down in the water. And if you're not careful, you might miss your fish. So what I'd like you to do is I'd like you to take a little break from the lesson, and I want you to try out your refraction labs 1 and 2 in this week's assignment. And I want you to make sure you write detailed and careful observations about each of these 2 labs. So I can go over the labs with you right now. Okay, so I'm just gonna go over a little bit of today's assignment and show you guys quickly how to set up the labs. So first question about refraction: when does refraction of light occur? So I've given you a little hint here. So when light travels through blank, it refracts. So you want to fill this in with however many words you need to kind of explain what refraction is. You can add some notes to kind of explain it down here as well. First lab, what you're going to need is you're going to need a coin, a bowl, and some water. I'm just going to do a quick little demonstration so you can kind of see me doing it. So bowl, coin, doesn't matter what kind of coin it is. I'm going to pop this down. I'm going to pop the coin into your bowl of water. You're going to get up, and then you're going to walk away as far as you have to so you can't see the coin in the bowl. And then what you're going to do is you're going to get a handy-dandy partner to fill up the water for you until you can see the coin from where you're standing. Okay, so that's lab number 1. You're going to answer the questions about the lab. So what are changes you notice as you pour the water into the bowl? So does your view of the coin change? So just answer that in as much detail as possible, please. And what do you think is happening by adding the water? So why does this change your view of the penny? So based on what we just discussed in the PowerPoint. Reflection lab number 2, you need a pencil, a glass, a cup of water, and oil. So I've got it off to the side. So what you're going to end up having is I've got a mason jar here, but you can use just a regular glass. You're going to pour your water in, and then you're going to pour your oil in, and then you're going to put your pencil in sideways, and then you're going to see if there's any differences when the pencil is in the liquid. Okay. So just overview of questions you're going to answer is you're going to draw a picture of the glass before you put water in it with the pencil. So glass with nothing in it except for the pencil, so you're going to draw that. You can post a picture or attach your drawing to this assignment. A picture or drawing of the cup with the water in it, so a drawing of the cup. And a drawing of the picture, a drawing of the cup with oil and water in it. So like you can see here, I've got my oil and I've got my water. Questions you're going to answer: what are changes you notice with the pencil as you pour the water into the glass? So your pencil stays in the glass, you pour your water in. What changes with the way the pencil appears? What was in the cup before besides the pencil? And then which liquid has the lowest density? So lowest density meaning that it is the lightest. Is it the water or the oil? Which one floats on top? And you guys probably already have seen my demonstration, so you should have an idea. Why do you think the pencil appears the way it does when the water is added? So you're going to refer back to the PowerPoint notes. Okay, So now that we've gone over our refraction labs, I'm going to talk to you a little bit about lenses, and then you can complete the last lab. Lenses are created to refract light in certain ways. So we talked about how refraction can cause different illusions. Sometimes we want to use refraction to benefit us, so we can see something more differently, or improve or increase our sight. So sometimes we use these things called lenses. If you are a person who wears glasses, you have lenses in your glasses. Contacts are a form of lenses. Everyone has a lens in their eye that helps them see. We also use them for different kinds of tools and devices like binoculars, microscopes, magnifying glasses. Those are all, we use lenses to kind of use all those things. So what exactly is a lens? It's a curved piece of transparent material. So sometimes lenses can be flexible. You saw last week that Jell-O can be used as a lens. So even though it is a very malleable material and you wouldn't want a pair of Jell-O glasses, any transparent material will work as a lens. Just like curved mirrors, we have two main types of lenses. We call them convex or concave lenses. So concave lenses has got the cave in it, so it goes in. Convex is the one that goes out. So concave goes in, convex goes out. And both of them have different ways that light is kind of bent through them. So when we shine a light through a concave lens, that light's going to be bent outwards, which is useful for some things. If we shine light through a convex lens, so light comes in, the light's going to be redirected inward. So it's going to converge. So this one's diverging, it's going out. This one's converging, it's going in. And both those things can be really useful for certain types of equipment that we need. So the image that you see on the other end of a lens, so when you look through a microscope or a magnifying glass, is dependent on the shape of the lens. So this is going to change your view. So when light rays pass through a convex lens, they converge or come together. So this is our eye. We're looking through a lens, so we can think of a magnifying glass as a really great example of a convex lens. So I'm looking through a lens, there's light coming through, which allows me to see. On the other end, we usually use magnifying glasses to do what? So we usually use magnifying glasses to make something look larger. So this example is a little small light bulb. So I'm looking through a little small light bulb through this magnifying glass. And then what happens is on the other side, I see this larger image of an object. So even though what I'm looking at is really, really small, what I'm going to appear to see, or what the magnifying glass is going to do for me, is it's going to make this image of the object look larger. Okay, so this is what the lens is helping me see. So I want to see this larger, then I'm going to use a convex lens because those light rays are coming together. So rays are coming through, they're being refracted, so they're being bent, but they're being bent inward. And that inward bend is going to allow me to see this image much larger. And then all those light rays are actually coming together at this thing called a focal point. This is really easy to notice when you think of something like a magnifying glass. If you hold a magnifying glass up to a piece of paper, you might have seen this before. Some kids burn ants, which is kind of cruel. But if you have light coming through a magnifying glass, what happens is it redirects it and it points it all together, right? So that's the same kind of idea here, and it's actually so powerful that you can redirect this light so much that it heats up and will actually start burning a hole in your paper. What's happening is it's a convex lens that's in a magnifying glass that's redirecting and refracting all of those light rays into a certain focal point. So things to keep in mind when you have a convex lens: images are typically larger and upright, though sometimes images can be upside down, which we'll talk about a little bit later. So uses for convex lenses. Magnifying glasses are great examples of convex lenses. Eyeglasses will have convex lenses if they're for increasing magnification. So like things like reading glasses where you can't see something, you want something to appear larger. Cameras If you're zooming in, that's using a convex lens. Microscopes are again for magnifying. So all of these things are used to make something appear larger on the other end. So this is an idea of exactly what's going on in a camera. There's lots of different types of lenses, but at the end you can see we've got concave lenses, but we also have some convex lenses kind of at the front. So all of these different lenses are going to affect the way the camera operates, but for zooming, you'd want a convex lens. Sometimes when you have an object that is a certain distance away from your magnifying glass, you can try this out if you have a magnifying glass. There'll be a certain distance. You can actually lift your magnifying glass further and further and further away from the object, and what will happen is the object will still get bigger, but it's going to go upside down. So the image will become inverted. So this is based on the distance of your lens to the object. So you can kind of play around with that. So if I move my lens over here versus over here, I'm going to have either an upright image or an inverted or upside down image. So you might remember this from when we did our microscopes. So high power lenses that are really close to the thing that they're looking at are going to actually make those images larger and upside down. Concave lenses. So concave lenses, what happens is the light rays that pass through the concave lenses are going to diverge. So they are going to go outwards. So my real object is quite a bit larger. What happens is the image of that object, so what I see through the lens, is actually going to appear quite a bit smaller. So my original object is large. This one makes it smaller. So concave lenses, the rays are going to be refracted outwards. So they go outwards, which allows me to transform this image into something smaller. And images formed are smaller and upright. This is not as important right now. The idea is that we've got light coming in through the lens and then it's going to be redirected outwards. Some uses of concave lenses. One of the most familiar ones, if you live in an apartment building or if your house has one of these, concave lenses are going to be on your eye peepholes in the door, which allows you to see more of your hallway and surroundings. So if there's a suspicious figure that comes to your door with a weird hat on, you can kind of see if he's got any buddies or anyone else is around. So it's going to widen your viewpoint. Another thing is eyeglasses to correct nearsightedness will often use concave lenses. Flashlights. So a flashlight, I want a lot of light to be able to bounce through them. Where is it? Yellow, looks like light. And I want the light to be spread out as much as possible so I can see more. So what happens is the lens in here, the concave lens, all right. The concave lens is going to spread out that light so it takes up a lot of room. So flashlights, door peeps, or door eyes, and eyeglasses to correct nearsightedness will use this. So as you may have noticed, eyeglasses use both type of lenses. Our eyes also have lenses in them as well. So when light travels through your eye, this lens inside of it is actually going to make sure that that light is redirected in the correct spot, which is at the back of your eye, where this information is going to be sent to the brain. If your lens is misshapen, what will happen, so if I had a really long lens, what will happen is that light could travel too far behind, which causes me to not be able to see, or too far forward if my lens is quite a bit too small. So your eye actually has a lens in it as well, and that lens can actually change size based on what you're looking at. So if you're looking at something that's right here, your lens is going to get a little bit wider so that the light rays bouncing off of it can be redirected and converge right on your retina versus if you're looking at something far away, light rays are going to go traveling through your lens. They're going to refract and they're going to be brought to your retina. So if something's far away, your lens is going to be a lot smaller. And if something's close by, your lens is going to be larger. So you may be asking, how does my lens move and do this? Your lens, and it's too bad we don't get to do our eye dissection, but I'm going to link one so you can look at it. Our lens is actually a malleable and bendable thing. So it actually changes size in your eye depending on if you're looking at something close by or something further away. So you can think of it a little bit as your own proper way of focusing on images. Okay, the third and final lab, what you're gonna need is a glass and a piece of paper to draw on. It's a part 1 and part 2 lab, but it's very, very straightforward. Oops. First thing you're gonna do is you've got your glass of water. You've got a picture of a smiley face. And you've got pictures of an arrow. What you're going to do is you're going to put them behind the glass. So I'm going to show you from what it looks like from my perspective. I'm going to put it behind the glass and then I'm going to look down and see what happens to the image. You might need to fiddle with, depending on the size of your glass, the distance of your image. So kind of play around and see if different things happen. My glasses are really round. They're going to have a different effect. So smiley face you're going to do first. How does it look like in comparison? Arrows you're going to do second. How does it look like in comparison? Outside, behind the water, not behind the water, okay? So you're going to answer these questions here. So describe or draw what happened to the smiley face after putting it behind the cup. You could draw a little illustration of before and after, that's fine. Describe what happens with the arrows. What does the water cause the image to do? So again, play with distance between the glass and your image. So the water is acting like a lens. What two things can we conclude that the water does to the image behind it? So it's going to do two different things. And then just basic things from the PowerPoint. What are some uses of convex lenses? You can take these directly from the PowerPoint. 2 uses of concave lenses. What are peephole holes? What lens do they use? And then microscopes. And that is everything. So good luck with your experiments. I'd love to see pictures. And good luck with your assignment.